time. Yeah. So good afternoon, everyone. Welcome to this September mini school. Yeah. And today we are very pleased to have Dr. Elena Caviglia as a speaker. Elena is a postdoc in the mathematics department here at Stellenbosch University, and she's working, which might not be a surprise, in category theory. Yeah? She completed her PhD at the University of Leicester not so long ago. And she and her share that we were born in the same city in Italy, if I remember correctly, Ella. So today is a very Genoa-based event. Yep. So, Elena, thank you very much for volunteering a mini school. And, mini schools that are survival guides are always very useful. So, Elena, thank you very much. Please start. And maybe at the end, the participants are welcome to ask questions, maybe using the QA facility at the bottom. And when Elena is done with her presentation, we can give you the permission, the right to ask your question in person. Yeah. So Elena, thank you very much. Over to you.
Thank you very much for this opportunity. So the idea of this mini school is to talk a little bit about two-dimensional categories. You will see that there are different kinds of two-dimensional categories. So my idea is to have a look a little bit at different kinds to see what are the differences, what they can be useful for, and to have a complete picture of what is there. Of course, I'm not going into technical details too much, but I hope you will have a nice overview of two-dimensional categories. But for today, what I'm going to do is I'm starting by recalling some one-dimensional category theory that will be useful in the following sessions so that we are all on the same page, and also so that we can really see the differences and what gets upgraded in dimension 2, what are the changes, and what are the main ideas. So I'm going to start from the very basics. So I'm going to remind you what category is. So we start with a category C. Category C has objects. Is it writing well? Yes. So we have objects. We can call them maybe X and Y and so on. And these, we say they live in C. And then if we take X and Y in C, we have a collection of morphisms between S and Y. So this is going to be a set. We call it C, X, Y, like this. Okay, so this is just a set. And what are the objects of these sets? We think of them as arrows between X and Y. So, for example, an arrow F from X to Y. So these are called arrows or morphisms of the category. And then we have a way to compose these arrows. So if we now have an arrow that goes from X to Y, let's call it F. And then we have another one from Y to Z, let's call it G. We also have a way to compose these two arrows. So we get an arrow from X to Z that we call G composite F. And this is the composite of the two arrows. So what we have formally is a bunch of functions. So if we fix X, Y, and Z, we're going to have a function from CXY cross CYZ into CXZ. And this function just sends the pair FG. It gets sent into the composite G composite F. So this is our composition, and we have similar kind of functions for every x, y, and z, of course. And then we have some axioms that this data needs to satisfy. So the first thing is that for every given every x in C, so every object in C, we must have a very special morphism that we call identity of x. So it's a special morphism in C of XX. So it's just a morphism from X into itself. And this morphism is special because if we now have a morphism from X to Y, for example, F, and we precompose it with identity of X, like this, what we get is simply F, right? This is what we normally see with also with functions between sets, right? So we have that if we now do F composite identity of X, this must be F. But also we can do F, and then after F we do identity of Y, and this is also F. So now we have that identity of Y composed with F gives F. So we have these unit laws from the left and from the right. And then we have that our composition is associative. So now if we have 3 arrows, we have F, we have G, and we have H. We can have 2 ways of composing these 3 arrows. We can do first F composed with G, and then we do H, or we can first do G composed with H, G, H, and then we precompose with F, and these 2 things are the same. So we have this associativity of the composition. And this is everything that we need to talk about a category. And now we can see some basic examples of categories just to remind ourselves. What are those? We have the category set of sets and functions. So the objects are sets and the morphisms are functions between sets. Then we can have more maybe algebraic examples. So for example, we can have GRP, the category of groups. And now we have groups as objects. And arrows are going to be group homomorphisms. So it's very useful example. And then we have also examples of maybe a different kind. So for example, we can consider a partially ordered set. So we have a set P with an order relation, and this is a category in which we have that objects are simply the objects of the set, and an arrow between, if we have like say A and B in P, an arrow between A and B is the property that A is less or equal than B. So between a pair of 2 objects, we only have 1 arrow if it exists, otherwise we don't have any. So it's a different kind of example category. But we have many more examples, of course. And now if we have two different categories, we can ask ourselves, can we maybe relate them? Can we compare them? Can we do something? And so naturally, we need to talk about functors. So these are maps between categories. So if we now have C and D, they are categories. A functor F from C to D is going to send every object in the category C to an object in the category D. So it's just a function sending X to f of X. Oh, sorry. F of X, which is an object in D. Now we can have another object Y, and it gets sent in F of Y. And now in the category C, we might have an arrow F from X to Y. And also these arrows gets sent into an arrow in D between F of X and F of Y. That is F of F. And these assignments respects the structures of the category. In particular, it has to respect identity and composites. So we have that F of identity of X is equal to identity of F of X. And if we have F and G that compose, we have that F of the composite of F and G is F of G composite F of F. And when we will talk about two categories, for example, or in general two-dimensional categories, we will see that we will find some axioms for functors between these higher dimensional categories that will look a little bit different from these. Okay, so we will see how it will go, but for now we only are talking about categories. So we have that composites and identities are preserved by our functors. Okay, and everyone who has worked a little bit in category theory knows that a very important concept is that of natural transformation. It appears everywhere in category theory. So let's recall this as well. So natural transformation can be thought as a morphism between functors, and we will see that this point of view is very important in two-dimensional category theory. But for now, what we have is that we have two different functors. They are both between the same categories, so say from C to D. So the picture is like this. So we have C and D, and we have two different ways of going from C to D, and these are F and G. Now we can define a natural transformation alpha, and this natural transformation alpha from F to G is a family of morphisms indexed by C. So for every object X in C, we have a morphism alpha X between F of X and G of X. So the family is indexed by the object in C, but it is a family of morphisms in D, of course, because F of X and G of X are objects in D, and alpha X is a morphism in D. And now, so we have this bunch of morphisms in D, but they need to talk with each other somehow. And so this is the condition that needs to be satisfied, the naturality condition. So if we now take two objects in C, say X and Y, and we have a morphism between X and Y, let's call it little f. We can consider alpha X, and we can consider alpha Y. For Y. And now we have that we can go from f of X to f of Y with f of F, and from g of X to g of Y with g of F. And this square needs to be commutative. This means that the composite of alpha X and g of F is the same as the composite of f of F and alpha Y. So this is the condition that needs to be satisfied for every morphism in the category C. We call it naturality condition. Okay, so now we know what a functor is, we know what a natural transformation is, and we are going to look at other things that one can do in a category that are very basic things in category theory. And for example, one of them is limits, right? Because then we want to see how this is done in higher dimensional categories. So let's remind ourselves how this is done in one-dimensional category theory. So we're going to talk about limits now. So, okay. So to talk of a limit, we need f, a functor, between a category D and the category C. And now we have to think that this category D is the parametrization of a diagram. Okay, so it represents the diagram of which we want to do the limit. And the idea of the limit is that the limit is what completes this diagram in the best possible way on the left-hand side. And we are going to see in a minute what this means. Okay, so the idea is that F takes a parametrization of a diagram and it sends it into C. So now we have this diagram, but embedded into C. It's going to be a shape in C, and we are going to see an example in a minute. But once we have this shape in C, what we want to do is we want to complete this shape on the left in the best possible way. So what happens is that, so if we now have a morphism in D, let's say we call the objects of D little I, little j, and so on, because they are like parametrizations somehow, so it's standard notation. So suppose we have a morphism F from I to j in D. What is going to happen is that this morphism F will be sent into F of F, from F of I to F of j. And this is a morphism in C now, F of F. Okay, and we can have a bunch of these morphisms, of course. For every morphism, for every object in D, we get an object in C, and for every morphism in D, we get a morphism in C, right? So we have a lot of these morphisms. Let me rewrite this specific one a little bit below because I'm going to use it now. So imagine we have a whole lot of these things. And now we want to find an object here, L, on the left. And this object must have connections to all these f of i's. So let's call this ci and this cj, for example, right? But there's a whole lot of them. So that's why we say that this is a cone, because like L can be thought of as the apex of the cone, and these morphisms, they form the whole cone. But now we want this cone to be universal. We want this cone to be the best possible cone, right? Of course, another condition that we have for it to be a cone is that all these triangles that are formed, like this one here, they are commutative. So Ci and f of f is the same as Cj. But this cone needs to be universal, and what does this mean is that if we now have another object A with a cone, let me here. Let's call the cone A, little a, so we have AI, we have AJ, and we have these things for all objects of D, of course. Now this cone must factor through the limit cone. So what it means is that there exists a unique morphism from A to L such that all these triangles commute. So for example, if we do AI, this is the same as this unique morphism. Let's call it, I don't know, L. AI is the same as LCI. And this is true for every I in D. So in this sense, this limit is a cone, and it is the universal cone, in the sense that every other cone must factor through this specific cone. Okay, and limits encode a lot of constructions that we might know from other areas of mathematics. And as an example, let us see that of pullbacks, because I really like pullbacks. They are very useful in geometry, for example. So let's recall pullbacks. Okay, what is the starting diagram for the pullback? So what is our category D like? It is like this. So we have two arrows both pointing to the same point, like this, okay? So now the idea is that our functor f, so this is our D, okay, let's call this maybe I, J, and K. So our functor f from D to C, we send I, J, and K to objects in C. So our picture, let's suppose that I is sent into A in C, and J is sent into B, and K is sent into C. And now we have that also these morphisms, little f and little g, are sent into. Okay, maybe the notation is not the best possible. Let me change the name of f and g, because now I want to call, I don't know why this g doesn't disappear. Okay. Oh, now it has disappeared. Good. Let's call this little a and little b, and we call f and F the image of little a, and G the image of little b. Okay, so now this was the parameter category, the diagram category, and now we have our diagram, but embedded into C. And we want to see how this diagram can be completed on the left in the best possible way, right? F, G, okay. So we want to find an object, let's call it P because it's going to be the pullback. And now we want to find a cone, right? So we must have arrows here. So let's call this PI. And then we will have our PK, right? Because our C was the K. And now we will also have this other arrow, PJ, right? So we have a cone. It's formed by these three arrows. But now what we notice is that since these triangles must all commute, so for example, PI and F must be the same as PJ, and PK and G must be the same of PJ, this diagonal arrow PJ is completely determined by the other two, right? Because it's simply PI composed with F, or also PK composed with G. So this arrow PJ, we can forget about it because it's completely determined by the other ones, right? But we will see that this is not always the case in two-dimensional categories, so we might need to remember these diagonal arrows. But for one-dimensional categories, this arrow from P to B, we can forget about. So now the pullback is simply P with PI and PK, and we want this square to commute because we want both these two composite to be equal to the PJ that we are forgetting about. And now the universal properties, so we need to say that this is the best possible cone. So we take another object D with a cone. Again, we should have a morphism from D to B, but we can forget about it because it's going to be the same of these two other composites. So let's call these DI and DK, right? And now there exists a unique morphism in ER such that the triangle commutes. And this is the universal property of the pullback that we all know and love, okay? So this is an example of a limit. Of course, we can talk about co-limits. They are just, we need to just dualize everything. So we reverse all our arrows and we can think of them as the best possible ways to complete our diagrams in the category, but now on the right-hand side, in some sense. And one important thing that we have to remember about limits is that they can all be constructed starting from basic limits, right? So we have this nice theorem in category theory that says that every limit can be constructed using products and equalizers. So this is a very nice result because it says that, for example, if you want to prove that a category has all limits, it's enough to prove that it has products and equalizers. So the work is much less. Okay, and the reason why I'm underlining this is that we will see what happens to this theorem when we go to dimension 2. Will it hold again, what kind of limits we need to have in order to construct all limits, and so on. So this is a nice result. Okay, but what I've just described is probably the way all of you have been introduced to limits. This is also the way I have been introduced to limits. So they explain limits to me like this, but it's not the only way, of course. And we're going to see an equivalent definition of limit. And the reason for this is that this is the definition that is more easily generalized to dimension 2. So this is the one we are going to see the evolution of in dimension 2. Okay, so in the same situation we had before, so this one, what we have is that we say that L is the limit of the diagram of the functor f, precisely if this happens. So if C is for every A in C together with a diagram with a cone, right? Sorry, forget about it. For every A in C, what we have is that C of AL, so the morphism in C between A and L is isomorphic. So, but this is a set, so we just mean that is in bijection with this other set that I'm going to explain in a minute. Okay. This one, now I have all my brackets. So what is this? This is this set. So we know that this set above, this is the set of morphisms in C from A to L. But what about the set below? So this is the set of cones, okay? But how is this the set of cones? So this notation means that we are considering the natural transformations between delta 1 is just the constant functor, into 1, the 1 category, and C and this other functor. Okay, so let's see. What is a natural transformation? From delta 1 to C A F. What are the components? So the components are indexed in 1. So the components are indexed in D. So for every I in D, we will have a component, right? And it must go from 1 to C of A F of I, right? This is one of our components, and we call it AI. So these are morphisms, right? But since we have 1 here, we can think of these as being objects in this category, C of A, F of I. So AI, in what it is in reality, it is an arrow from A to F of I. So these arrows from A to F of I are precisely the ones that form the cone from A, right? The one that we had here on the left. And the naturality condition of this natural transformation is precisely saying that if we now have 2 of them, right? and the morphism between them. So if we have, let's write down the natural transformation conditions. So we have A, I, and J, and we have a morphism F. So we have AI and we have AJ as well, right? And now we have the image of F under the constant functor. This is just the identity. And now we have F of F, right? So this square is simply one of these triangles that we had in the cone, right? Sorry, it's not written in here. It's AI and F of F is, it's kind of written in here, but it's this big triangle there. Okay, so what is this weird category of this weird set of natural transformation? What it is in reality, it is just the set of cones. So this condition that we have here, it's simply saying that every cone just corresponds to a morphism from A to L, this little l. So it's explicitly saying what is the universal property of the limit. So this is a different way of seeing it. Maybe you have already seen this, but it will be important because what we are going to do for two-dimensional categories is to generalize this kind of property. Okay, right? And so I think this is everything I wanted to say about one-dimensional categories. So now let me say something about what are the ideas that we can use to construct two-dimensional categories. So we start with a category. Imagine we start with a category C, and now we want to find a way to make it higher dimensional, to make it two-dimensional, right? So what category theorists have found are two different ways, two different constructions that we can make with a category C. Okay, one is called enrichment. And what is the idea of the enrichment construction is that now, instead of having a category that has OMS sets, so the set of morphisms between C and between X and Y to objects in C is a set, we can have that this is instead an object of the category C, right? So for example, if C is an abelian group, we can say now we consider categories in which such that C of X, Y is not just a set, but it is an abelian group. So it has a multiplication, a structure of group. But we can do this in many different ways, right? We can enrich over many different kind of categories. Okay, so if we enrich over the category C, we obtain what we called C categories. So it's a way to, starting from a category C, to construct some kind of other categories that are related to C somehow. But we can think of a different, completely different approach, and we can think of an internalization approach. So instead of now changing our OMS, what we want to do is we want to take the category C, look inside the category C, and construct categories inside this category. So what we get here are categories inside C. So they are still categories, but they live inside the category C. It's like we take the category C and think that this category is the whole world, and now we want to study categories in this world. Okay, so these are two very important kind of constructions in category theory. There are a lot of people studying enriched categories and internal categories. And now we can do this procedure, but with a specific categories that is cat. So we haven't introduced it properly, but we have spoken about it. So if we consider cat as the category of, okay, I should say small categories, but we don't care too much about size issues in this context. Small categories and functors between them. And now we can say what happens if we enrich over this category. So what happens when we consider categories such that their OMs are categories, right? So we can consider cat categories. If you think about it, we are saying that now if we fix two objects, so if we fix two categories, C and D, and we look at the set of functors between C and D, this is not a set anymore, this is now a category. So we mean that that we have a two-dimensional level. So instead of just having objects in our categories, we have objects and morphisms. We now have morphisms between morphisms. And this gives rise to what we call two categories. So we'll talk about it next week. So the idea here is that we have a new higher level, right? We have morphisms between morphisms. But we can also take the internalization approach and we can consider the categories inside the category of categories, right? So if we use our notation from early, this is going to be cat. Categories internal to cat. And in this way, what we find is interesting because it's a different two-dimensional structure. So what we find are double categories. Double categories are categories inside the category of categories. And we are going to talk about double categories as well in the next weeks. Okay, and now in the framework of two-dimensional categories, we also have bicategories. And bicategories are simply two categories, but a little bit weaker, okay? And we are not going to focus a lot on bicategories, but I'm still going to say something about them so that you have a complete picture. So we have two categories, we have double categories, and we will also touch on bicategories. Let me write them. Yeah. So this is everything I wanted to say for today. So if you have any questions, I'm happy to answer while I try to write by categories. And thank you very much for listening.
Thank you very much, Elena, for the very nice talk. And I think we have a few questions in the chat, or one question in the chat, and I think one question okay, the question in the Q&A is about handwriting. That probably has been solved. Yeah. But maybe let's do the following. Let's ask Dario to ask his questions in person. I will quickly make Dario a panelist and give him, here we go. So now Dario, if Dario unmutes himself, he's welcome to ask the question in person. Yeah, please, Dario, go ahead. Hello?
Hello?
Yeah, hi, Dario. Please ask your question to Elena. Welcome. Yeah.
Hey, Elena, thank you for the wonderful presentation. I was just wondering, so we have these two constructions, two categories and double categories, and then you mentioned we'd also briefly touch on bicategories. Are bicategories of a multi-category?
No, they are not multi-categories. They are a weaker version of two categories. They call them bi just because two was already taken, I think. Like they wanted to say two somehow, but two was taken. So we will see that they are not enriched categories because there is nothing you can enrich over to get them, but they are weakly enriched somehow. So the idea is that we allow, because now what happens with two categories is that we can have arrows between arrows, right? And so the idea with bicategories is that we don't need the composition to be strict, but it can be weak. So we can have that. Yeah, the associativity, for example, we can have that it's not true that the composite of F and G and then H is the same as F and
right,
then
but just up to some transformation.
Yes. Yes.
Okay, I understand. So that's sort of a separate, so multi-categories are yet a different thing from everything we're talking about here.
Yes.
In a certain sense. Okay, all right. All right, yeah, thank you.
Thank you very much, Dario. Are there other questions or comments for Elena? Elena, I think, sorry, Elena, would you like to add something?
Yes, sorry. I just wanted to say that if there is some particular aspect that you would like me to cover, I'm happy to do it because I will need to choose something. There are a lot of things that are done in two-dimensional categories. So if you are interested in a specific topic, please let me know. So maybe in the last meeting, we can also touch on that.
Perfect. And in the meantime, Joseph Attaglie has a question, and I just promoted him to panelist. So Joseph, if you would like to ask your question in person, you're most than welcome. Otherwise, I can read your question. Just unmute yourself, Joseph, if you're still here. Perfect.
Hello.
Hi, Joseph, we can hear you. You're welcome to ask your question. Thank you very much for joining us.
Okay, thank you, Elena, for the talk. So I wanted just to ask, how can I define a natural transformation in category?
Inside the category, you mean? Like in internal natural?
Yeah. Sorry.
So if you have two internal categories, now you can define an internal functor between them. And yes, you can also define internal natural transformation.
Okay. Thank you.
Excellent. Thank you, Joseph. Okay, if there are no more questions, thank you very much to everyone for taking part. I see lots of compliments in the chat appearing now, Elena. So really much appreciate your very nice lecture. And I think everybody is looking forward to see how the story continues. So I think we will meet again here next week, Wednesday, again at 2 p.m. And please keep in mind that Elena offered to react to your wishes. So if you have questions, suggestions for topics that you would like to discuss, please get in touch with Elena or with me, and I can forward it to Elena. Yeah. So thank you very much, everyone, and have a nice rest of the day. And in particular, thank you very much to Elena. Thank you very much, Elena.
Thank you.
All
Bye.
the best. Bye. Bye-bye. Bye-bye.